Well, special thanks to Taiwan for its leadership and support of Cosmic 1 and 2. And that's the end of my history. Thank you very much.
All right, thank you, Rick. So I believe Tom is the next speaker.
So it's good timing. Thanks, Rick. That was a fascinating trip down memory lane for me. I'm not going to do pictures or slides. I'm going to tell stories and try to keep it brief. How am I doing on time, by the way? Are we running late or do we have enough time? Okay, great. So I don't have slides, but I brought a prop to talk about GPS Met. And it's GPS Met. This is the flight spare that was intended to be flown if the primary didn't make it past the vibe and thermal vac and that sort of thing. It's been sitting in a cabinet at JPL for, I guess, about 30 years. But managed to find this. So I'll talk a little bit about this, what it took to get here, what my experiences were, and I'll do it in 10 minutes. So my first contact with the project that would become GPS Met was a call I got in 1993 from a guy I didn't know, Mike Exner, about a NASA mission that I did not know about, which was Microlab 1, that indicated that basically he was asking if JPL wanted to consult on a radio occultation mission that UCAR, a company that I was familiar with, but I believed had no flight hardware experience at all, was going to do. So probably before I go through what happened after I took that call, I should give you some context for the times, essentially, as I recall them. Now, bear in mind, in this talk, it's I'm going to hope to get like 70% accuracy here. And Rob's going to come up after me and maybe he can fill in the other 30% or correct my 70%. I'm not sure. But this is in the early 90s, late 89, 89, 90. It was a pretty rich time for, I think, GPS technology development. I think people, at UCAR would, especially working at UNAVCO, would say the same thing. And that is that GPS had sort of come into its own in the sense that there are instruments being built that were designed to do fairly precise and accurate science. It was mostly Earth-based science, and there was a number of applications. And a lot of the work was involved in sort of trying to fill out what those applications might be, what's the most useful thing, with a couple of explicit things that came to mind and were being worked on and funded. And that was geodesy primarily. But at JPL, we were interested very early on in trying to put an instrument. It is part of our business to do things like that, trying to come up with applications that were related to, first of all, precise orbit determination was one of those things we started working on from an early time in the late 80s. And then applications for direct science, and radio occultations was just one of those. For me personally, aside from working on a number of ground-based initiatives for geodesy that were things like doing precise geodesy from a moving platform, from an ocean platform that was also essentially sounding the bottom of the ocean and doing tectonic measurements and fault line measurements using sonobuoys and things like that, to aircraft attitude determination. Personally, I was much more interested in doing a reflections instrument from space than I was doing a radio occultation instrument from space at the time. And a lot of that had to do with I didn't know very much about radio occultations. But I'd say that the atmosphere at the time, we were very familiar with working with UCAR, was more contentious than collaborative. I think we were both sort of working towards the same pool of money roughly. A lot of the projects overlapped. And we were competitive about, who had the best processing. And so it was clear to me anyway at the time that, let me put it this way, it was unclear to me that we would ever cooperate or collaborate with any kind of a mission, especially a space mission with UCAR. And so when I got this call, it's basically talking about the mission and what they were proposing. And this was, mid 1993, I think, when Mike Exner called. I guess my primary attitude was, so, okay, so what? So you want us to collaborate on something or consult with something? And I'm thinking, we got so much to do. I don't know why we would bother. And we were definitely interested in radio occultations, but we were pursuing our own path on that. As you heard Rob point out, we had we'd already identified microsat possibilities that were in the queue to essentially do a first radio occultation experiment. So it seemed like more of an impediment to do GPS MET, or at least to participate based on what I knew so far. And also, I was pretty sure from talking to Mike Exner that we were not a first choice to work with. I think the goal was, I think, to get some experience from JPL because they wanted to use the industrial supplier that we had used to do an instrument that we had designed called the Turbo Rogue. And that supplier was in Southern California, Alan Osborne Associates. And I think his proposal was, look, we want to buy one of these instruments from this company and put it on a spacecraft. We want you to, basically consult and talk to us about, if there are things needed to do that and that sort of stuff. And early on, we had written an exclusive contract to Alan Osborne, giving them all the rights to all the software. They had all the source code, and they developed the hardware. And we weren't, working with them too much on anything because basically the Turbo Rogue was a successful instrument. We were moving on to other things. But the question I asked Mike was, what do you expect Alan Osborne to do? And he said, well, we'll need some modifications to get it to work in orbit and to schedule occultations and to deal with, all the things related to that. And I said, well, there's two problems. One, they don't know anything about the software. They have a copy of it, but that's a lot different than actually knowing how to operate it. And the other thing is they don't have the rights to anything above Earth. In other words, all the flight capability was written out of the contract specifically. They could have ground-based rights to the software, but they couldn't develop an instrument for space. So I think that was, I think Mike was quiet for a long time after he heard that. And it was later that he called back and said, okay, so what are you proposing? How can we make this work? And that was what sort of started the process of, okay, here's what's needed. I had to talk to people, my bosses, to see if we wanted to participate in this. And there was a lot of potential problems coming from people at JPL at the time. I don't even know if Rob was fully on board early on with this whole idea, but I know everybody wanted to see this happen in terms of to get the first, the first occultations. We all believed it was inevitable, and we all believed it was important science. But there's a thing that happens with groups when you're first needing to trust each other to move forward. And we were at that inflection point, I think, with this discussion with Mike, the fact that he or somebody at UCAR came back and said, okay, let's give JPL a bigger piece of the action. And also from the JPL side, in terms of, okay, let's go ahead and collaborate. What harm could it do? It probably won't happen, and we have our own irons in the fire, so we'll pursue those. Once we got started, there were several problems that popped up with trying to use this instrument in space. And one of the first problems was I didn't know anything about doing a space instrument. And I was in charge of this particular aspect of it, but I could draw on a lot of people at JPL who could help me. And the first thing we did when we tried to put together this assembly, which is in an odd form factor, which I'll talk about in a second, was we modified, we had Allen Osborne Associates, this company, basically strip out all the ground-based things, the displays and things like that. And then we fit this thing into a box and mounted it such that things were stable. Meanwhile, we're writing software and trying to figure out the things we needed to make this work. The big advantage to this instrument was it was based on a platform that was a very software-centric instrument, and that was unlike any of the other geodetic receivers of the time. We had a very powerful, at the time, 20 MIPS processor, which was unheard of for a simple instrument like this. And I just looked it up, and 20 MIPS is 0.1% of what my watch has. But it was powerful for the time, and powerful enough to have software-driven tracking loops that we could easily turn off when the SNR got too low and let them coast as long as possible to continue to collect data after it wasn't possible to basically be phase locked anymore. That was the first problem. The second problem was we had electronics that it turned out were not good enough for flight. And this form factor was a problem because it stands up, and you'd never build a box for space flight and mount it like this. But the only space available on Microlab 1 was a very small little box because we were not a primary payload. The primary payload was a lightning sensor from Marshall Space Center. And so the first time we vibrated this thing standing up, the first thing that we would test it before and everything was working, we would vibrate it, we would take it off and test it again, and it required nothing. And the oscillator broke because it's sitting up high here, and it's getting way exceeding the possible vibe limits that it could handle. So we quickly found the manufacturer, talked to him, and said, "Can you make this more rugged?" And they said, "Oh, you're putting it in space? You're not supposed to do that." And so they did that. This is all my aptitude for space instruments was not very high at this time. They did that. Everything else passed. And we finally got to the point where we had an instrument that worked on the ground. I think UCAR was the other changes we were trying to make to it is we were envisioning this as something we would need to make a lot of modifications on because we did not expect it to work. So the software was modifiable post-launch. And we didn't know what might not work, but there's just a lot of unknown about that. And I think one of the most surprising things post-launch, and this is only an 8 satellite receiver, so it has, and we have an antenna that's looking out the back. So we had to do POD at the time, as well as schedule occultations, and we had a very simple algorithm. We basically, any satellite we were tracking, we would simply have a certain data rate at a certain altitude, and then we would change the data rate when it got a little bit lower, and then the data would go to high rate once it got down to about 60 kilometers. And that was when we actually started the occultation. The occultation would run just for a number of seconds, regardless of the SNR. And then we would try to basically fill gaps when the SNR was too low by coasting and letting it continue to produce good phase data after the fact. And this sounds, I mean, this is like the first attempt at sort of an open loop model where basically we just used the previous model. It worked best when we used a ground-based approach we had used with one of these earlier ground applications, and that was where we wanted to drive along in a vehicle and precisely survey a freeway. We had built, with the TurboRug, we had put together an application that when you went under a bridge, it would shut off the tracking loop, stop feeding things back, and then as soon as the SNR came back up, it would close the loops again and continue. So essentially this bridges mode became the means with which we were able to get a little bit lower in the atmosphere when we had ducting, because we have a duct that lasts roughly 10, 15 seconds, which is about the time we happen to estimate we would be under a bridge. And that turned out to work fairly well. The most surprising thing to me about GPS MET, the instrument, was that from the very first occultation, after we turned it on, it worked. We didn't have to do anything to modify it. We still modified it to try to do various other things with it. The other thing that was surprising is that we managed to get the Air Force to turn the GPS constellation into a non-encrypted mode, which would be tough to do now. But because JPL was working with the TOPEX Poseidon project, TOPEX did not have a P-code receiver that could do encryption. It had a P-code receiver, and we needed that for altimetry. We got a special exception from the TOPEX project manager, basically contacting the Air Force and saying, okay, you give us a 2-week period and we will turn off encryption to the entire constellation. And then at the end of that 2 weeks, we're turning it back on again. And so in the GPS MET data, I think if you look carefully, everything is primarily these 2-week intervals, and that's why. And that basically happened from having the access to somebody on a project who had access to the GPS constellation, which had not gone operational yet. It would never would have happened if it had gone operational, and they would just cycle it on and off as we needed it. Lastly, probably the most important thing to me that came out of it was the deep respect I had for the people I worked with at UCAR, and the understanding that, how important collaboration is, how important it is not just for this individual project, but for years ahead. And I will say, there were people at JPL, one in particular, who actually wanted us to kill this project partway into it. By kill, I think what I mean is just to lay it long enough for JPL to get one of its instruments in orbit and do the first occultation. And of course, I think we made the right call by telling him, no, we're not going to do that. But that's, that was the understanding of the stakes. And that was also sort of the mistrust that took place, I think, at the time, and why it's important to try to overcome those challenges. And it's probably the thing I learned the most, the thing I got the most out of from the GPS mission. Anyway, that's all I have to say.
Well, you heard the young Kaczynski talk. Now we got a real Kaczynski current day.